welcome everyone to this talk about static code analysis. Actually, this is sort of a journey of a tale of the journey I've been on. I've been building static code analysis tools myself for a while, and this is sort of, I want to take you along on the ride. What's hard about writing code analysis tool? What goes on under the hood? What's the tricky stuff you need to do? And on the way, apart from learning and having fun, it's also, well, it'll help to understand the challenges and look at tools and see to what degree which of these challenges they actually deal with. And I always like a talk to be interactive, so if you have questions, just go ahead, raise your hand in the middle, rather than at the end, because questions usually are better asked and answered right away. So, static code analysis. What is static code analysis? In its simplest form, static code analysis is just command line tools. We've all been there. We can look at all files there and look where an invoice service is being used by grep, or we can look at how much test code there is in our project. This is definitely useful, and this is static code analysis, and it's valid. And sort of none of this stuff is the right way. It's just solving different problems at different levels. So this is definitely useful. We've all done it probably, but it hits limitations. For example, if we want to do cross-referencing. If we want to figure out, we have a field p.name. What is this actually? Where is this defined? So we will need to understand that there's a concept of a type person which has a field name, and that this p.name refers to person.name and not city.name, which is indistinguishable at the source code level, at least per line with a non-understanding. So we need some insights, some data structures about what goes on inside the code. And usually, this is typically called an abstract syntax tree. So we could start parsing the source code, and we could have statements like assigned statements, method called statements. We could have expressions inside these statements, and then have higher level constructs like methods, classes, etc. And we could parse the source code into these representations. And the examples here, I'll use Java examples because it's pretty well known, but most of the stuff I'm saying applies to basically any programming language. So it's pretty general, it's pretty applicable across the board. So in order to answer questions about cross-referencing or any deeper understanding, we need some sort of data representation in memory of the code, some sort of here object-oriented representation of the code. And if you want to play with this, there's open source parsers for the Java language. Basically any parser generator has a Java grammar as one of its samples. So let's say we have this representation. I'll stick with the source code here, but just sort of to keep in mind that we have data structures that allow us to reason about this. We have a field access expression with a base variable of p and a field name of name, which is great. Now we know it's a field, but what does p actually refer to? It can be a lot of things. It's non-obvious what this means. It could be a local variable, so we need to go look backwards and see if it's a local variable, but it isn't. It could be a class name in the same package. It could be a class name that's imported. It could be a static variable. None of this. But checking all these in the right order of precedence, we find out it's a method parameter that's declared in the signature of the method. So now we know P is there, and at that point we see that person is the type. But again, person can be any sort of type. We still need to resolve this. We need to look at the import statements, or it could be a class in the same package, or in the default package, all these kind of niceties. So going with the source code is pretty onerous. It's not as straightforward as you'd like. You need an incredibly deep understanding of the intricacies of the language in order to figure out what this is. This process is typically called linking, sort of making sense of identifiers. It's possible, but not necessarily what you'd want to do. And you need to support all the syntactic sugar of the language. I mean, even Java does have syntactic sugar. Other languages have way more syntactic sugar. Type inference, for example. If there's var, you need to figure out what type is behind that var. Or if you have a lambda, then you need to figure out that this lambda has the type supplier and that there's a synthetic class of this type. All these stuff that Java does at runtime by generating code using the ASM library at runtime. You need to figure out what it does there. Or also the additive types, sealed classes with all their weird semantics and stuff. This is all stuff you'll need to understand or build understanding into your tool in order to be able to reason about source code. But there's a better or a different way that doesn't have these shortcomings. You can look at binary code, at byte code. So you could parse class files which did all these things. Class files are desugared, they have full type information all over the place. They have their own challenges. I mean, just having this code here means stuff is resolved. You need to go into bytecode, and if you go into invoke dynamic for string concatenation, becomes even more interesting. So those are basically the two approaches. You need some sort of object-oriented representation in memory in order to reason about your code, and you can either go with source code, or for languages like Java, you can go with binary code. So which is the better choice? That depends, obviously. I mean, if there's two choices and not just one, usually means that both have their place. If you want to, it depends on what you want to do. If you want to reason about code layout, comments, etc., or if you are interested in fault-tolerant parsing, if you're part of an IDE already, that means source code has advantages. Source code allows you to have smoother representation of the results. Bytecode is usually more efficient, and you can leverage all the support of the compiler. So most or many tools go with bytecode because it doesn't force you to keep up to date with the latest version of the language. It's more robust in terms of backwards compatibility. Okay, so now with these data structures, it's sort of easy to understand how we could reason about places where person.name is used. We could just look at all field accesses and then figure out what the variable is, what type the variable has, and if the field name is name, then we'll know it's used there. So this is sort of the first hurdle to take. Some sort of semantic representation you can reason about in memory rather than just having text representation. But obviously, we can and want to go beyond that. So the next step is reasoning about code flows, execution flows. It's not just the type information statically, but oftentimes many things rely on how code flows or how execution flows through code. So the domain I come from is the security domain, so that's where the examples come from. And this would be a classic SQL injection. We have a variable s, which is initialized from an HTTP header, which is untrusted. It comes from the HTTP request, and that is used in a JDBC connection prepare update statement, or a prepare statement, which means obviously it can do anything with the database. We don't want this. So what do we need to do to figure out if this is vulnerable or not, if this is actually a taint flow? So the same sort of logic applies for figuring out if variables can be null or if resources get closed, etc. It's just that this is the domain the examples are from. So in order to figure this, we need to look at this variable and see where it is used. We know this variable has an untrusted value, and then follow through the code and see where it is used. In this example, that's pretty straightforward, and we could just do some naive implementation and get away with it, it would work. Becomes trickier in real-world code, of course. The variable can be reassigned to another local variable or as a field to some object, or and then read from there. So this requires semantic understanding of what these statements actually do and how they propagate data. If we want to track flows, execution flows, we need to know or teach the analysis tool what sort of data propagation happens, where data flows. Still, this looks like it's onerous work, but it's still sort of straightforward. Becomes a little more interesting if we add propagators to the mix. Propagators are method calls that do stuff internally that we don't really understand, that are too complicated for us to understand, but that we treat as a black box. For example, string concatenation. So we have some raw data that's from a header, and then we have a string concatenation with some literal and this untrusted part. So it's a different variable, it's not just assignment. So we need to know that string concatenation means that if either of the input parts is untrusted, the result is untrusted. And there's actually quite a lot of these, like substring or all the Apache common slang stuff, string modification. So this is the first part where domain knowledge enters the mix. Still, it's sort of doable. So far, it's pretty deterministic. I mean, we need to teach our tool about the different kinds of propagators, but if we do that, we can reliably report whether there's a flow or not. So, enter conditional flows. Let's say we have a conditional, if a header is null, we use a safe string, otherwise we don't. And then we use the result. This means that, well, there's a condition which we can't really reason about. In static code analysis, the most common case is that we don't really know which of the branches of an if statement will be hit, because input is usually outside our control. We don't know if request.getHeader can be null in a given scenario. I mean, in this case, we could sort of add domain knowledge about HTTP headers, but usually it's hard to reason about. So essentially this means we don't know which of the branches is taken, so the best we can really report is maybe. So there may be a path that is vulnerable, there is maybe a path that's not vulnerable, and so the usual approach is to say, as far as we can determine, there is a vulnerable path, so we report this, we treat this as a vulnerability, because there is a valid vulnerable path. The same happens if, well, here it's more involved. We have a condition that really outside, I mean, system timer is outside our control, and so there can be several conditional executions that can be combined. So up here, S can be either safe or unsafe, and it can be used in different paths down there. So we have 4 combinations. And this can actually explode, and usually does, if we just naively look at all combinations. This seemingly harmless code takes in the header, and then the first if has 2 different paths. None of them have any impact on what we're doing, but still it's 2 paths. And then the next line multiplies that by 2, so we have 4 paths. And overall, we have more than 1,000 paths, different paths through this method that we need to track. So this can really, really blow up. That's the It's called combinatorial explosion, and that's basically what it does. Just naively looking at all combination, at all possible paths, is infeasible for any non-hello world code. So we need to start approximating. And actually, it's mathematically proven that static code analysis can't be correct. There's no way to determine how a program behaves. It's not sure what's in English, Haltetheorem or Halteproblem in German. There's no way to write a program that determines if another program terminates, that sort of thing. So we need to make approximations. And this is where it becomes tricky, yes?
The halting problem.
Halting problem, thank you. So we don't want to look at all these more than 1,000 paths, especially if they don't do anything. They're totally irrelevant for what we're interested in. So one common solution to doing this is merging. Here, the idea with merging is that when two branches merge, we treat them as one single branch with either or. So here we'd have, at this point, we'd say S is, we just continue with a single flow from here, saying S can be tainted, S can have untrusted content. And just move with a single flow from here. So with this example, it would mean that we'd have two different paths through each of these lines, but after each line, we just treat them as another, just as a single execution. So it's additive instead of multiplicative, so that we don't have 1,000 paths, but 11 paths. Because we just, we go with two paths through each line, but afterwards we merge them. This is pretty powerful in getting a grip on complexity, on terminating in finite time, but it comes at a price. The first condition is S is maybe tainted, because it's tainted or maybe safe. And then at a different point, we know the condition, we look at the condition, it's the same condition which we ignored, and we go through either call this or not. And since we merged here, there's no way we can ever see that this is safe. Because if the condition is true, S is safe, and only if the same condition is true, S is used in a dangerous way. So merging means we give up precision for speed, which is one of the typical trade-offs we have in static code analysis. So we're going to look at refinements of this. One interesting thing to statically analyze is loops, because we go through the same code several times, but with potentially different values in the variables, which is not something we can just cover with our naive approach we had so far. So in this case, in the first go, only C is tainted, but then in the assignment at the beginning, B becomes tainted, but A is used. So it's safe on the first go, but then in the second pass, A is assigned the taint from B. So only if we go through this loop, if we scan through this loop twice, do we find the vulnerability. But still, we don't want to just scan any loop an infinite number of times. So it's important to figure out how to terminate this. One naive approach is to just limit, to have an upper limit of the number of times we want to go through the same code. And there's better ways, but that's the naive approach. And obviously, we need some sort of solution because we don't want to go through code just once, and we don't want to go in an infinite number of times. So having a finite upper limit is a pretty common, simple compromise. And just an illustration that it is impossible to be fully precise in static code analysis. Here we have a taint in variable s, have a number n. I mean, this is the 3n plus 1 problem, essentially. So we don't know if this code ever reaches or is guaranteed to reach the update because, yeah, this is one of the classic mathematical problems that are unsolved if this always gets to 1. So far, all the stuff we've been looking at has been inside a single function, inside a single method. So let's look at what happens if we do add function calls to the mix. So we start with a method that taints s and calls source for a method and then puts the result as a parameter into sync. Source takes the HTTP header, sync does the prepare statement call. So and these are static methods, so deterministic and clear where the calls go. And essentially, for these kind of function calls, we could just treat them as inlined. Just scan through them with the variable name mappings, but essentially scan through them as if they were inline. That's the simple part. There's no big challenge there. Things become interesting, of course, if we add recursion. Sort of similar to the stuff we had with loops. Again, we can shift stuff through variables so that only after, in this case, two recursive calls, do we actually hit the vulnerability. Same problem, we need some sort of limitation. If we just merge naively, we'll lose this because we don't, we'd hit the same line twice and get rid of it and terminate. So this is pretty similar to the loop thing. Virtual method calls make things really interesting. Big challenge for static code analysis tools because polymorphism is essentially, the goal of polymorphism is essentially the opposite of static code analysis. Static code analysis is about looking at the caller, at the code that does the call, and figuring out and being precise about what it does. Whereas polymorphism is about hiding this and making it hard to figure out at the side of the call. So in this case, we have an interface with the method doIt and two implementations, A and B, one of them safe, one of them dangerous, and we call that polymorphically. And essentially, we have no way of knowing which of them is called here. So sort of fan out is the reasonable way of doing this. Sort of, it might be either one or the other, so it's either or. It's sort of similar with a conditional. This, however, it's not as straightforward that this is easy, or this makes sense, because the result of scanning my service depends on what else is on the class path. So if we add class B to the class path, we have a vulnerability in my service. And if B is not on the class path, this changes the result, which can be surprising. So it's sort of subtle side effect here. One typical approach to dealing with virtual method calls is to create a call graph up front. So if you ever hear or read about a call graph, this is where that comes into play. The idea is to look at the calling code, so the invocation of c.accept, and figure out which implementations it could go to. With the naive approach we just have, it would be both. So it would be both safe and not safe. But in this concrete case, we could look at the code before or surrounding the invocation and see that C actually is initialized with an instance of safe. So in this case, we could construct the call graph to know that it's only the safe variant that can ever be called here because it can't be the unsafe one. The reference C is actually the consumer, but in this case we know the concrete subtype, so we can construct a call graph this way. Yes?
Would you not want to know that there is a risk that at some point you might include not safe?
The question is, don't I want to know about the risk of at some point including the not safe? It depends on what kind of analysis you're doing. But the usually you want to reason about the code as it is. And in this case, actually there's a constructor, new safe, right before the invocation. So, and as long as you don't change that, adding a not safe would not change anything. But yeah, good point. There may be scenarios where you want to reason about potential changes. But usually it's about the code as it is. So building there are better algorithms, better ways of constructing the call graph than naively going for all possible implementations. You can take into account the code before that and reason about the subset of subtypes that can actually be behind the reference. Still, it would be from the call side, based on the call side statically to wherever it goes. But this is limited. So let's say we have code like this, where we have two branches. One of them has a tainted variable s, but a safe implementation of the consumer. And the other initializes s in a safe way, but has the unsafe consumer. And if we merge this, there's no way, if we just use a call graph here, well, we know that s can be tainted or not tainted. And based on the call graph, C can be not safe or safe, so we'd report a vulnerability, which would be a false positive. So in order to avoid this false positive, we need to reason about the flow. We need to correlate the taint and the type of the consumer at the flow. And this is something that can't be done with a call graph up front. So this is stuff that will always create a false positive with a static analysis tool that's based on call graphs. Call graphs are inherently limited by this. Another aspect of, or another thing that's tricky to do and that makes static code analysis interesting in a good way is aliasing. So let's say we have two string builders, one string builder with two variables pointing to it. And so B and A are the same object, but different variables. So, and we append something to A that's unsafe, and then we use B in a different place as a SQL string. Then we need to, in order to see that this is a true positive, that this is vulnerable code, we need to be aware that A and B are actually the same thing, which can be due to some assignment in a totally different place that took place a long time, totally different part of the code than where we started knowing that there would even be a taint involved. So tracking of aliases is one of the really tricky and expensive things to do. Tracking all aliases all the time is prohibitively expensive if done in a naive way, because we can't just globally track which variable is aliased with which variable, especially if you have flow sensitivity to the mix. So there's sophisticated algorithms around this, like querying backwards where in the place where the variable is used to figure out what potential aliases there are. But this is really tricky, especially since, we are doing stuff like merging, so yeah. And I'm not presenting any answers here. It's just, this is one of the tricky stuff. And this is something to check if you want to sort of crash or find the limitations of a static code analysis tool, working with aliasing is definitely one place to go. So, so far it's been about the technical side. And there's way more that I can't go into here, like reflection and stuff. But there's other parts that I'd like to point out that are highly relevant for static code analysis. One of them is framework awareness. It's tempting, or I mean, we're all geeks at heart. So if we start writing a static code analysis tool, what we care about is the algorithmic side, the stuff we've been talking about so far. But in order for this to have real-world value, it needs to be aware of the details of frameworks. For example, with Spring, there's a put mapping here. So we know that this is actually a part where we should start scanning. We know that we see that this request produces application JSON, which means it's not vulnerable to cross-site scripting because it doesn't generate HTML. And we know that the request body, the annotation at request body, means that this parameter is tainted because it was JSON deserialized. And this just to give as a simple example, and this sort of framework knowledge is totally unsexy. It's not really tempting for us geeks to do, but it's highly relevant for creating static code analysis tools. Static code analysis tools, good tools, aren't just about solving the algorithmic things. That's sort of what academia does, where academic papers are great, but it's about doing the tedious work of getting framework and library details and actually domain knowledge into the tool. One big area that's part of the user experience of static code analysis tool is figuring out which findings are unique, which findings we actually want to have reported as separate findings. I mean, in this example, we have a single header that's being read, and then we have we have a conditional flow that uses this as a SQL update in both cases. Probably something we'd want to see reported. Not totally sure, but this is pretty much on the end, yeah, this makes sense. But what about this one? We have a single header, and we have conditional flow that modifies this in different ways, and then a single SQL update. Do we want to report this? No, totally sure. Becomes more vague. And then the typical SQL string building pattern. We have a single taint, and then we have a SQL, lots of conditionals that modify this, and it's used. We'd probably not want this used as reported as several findings because it's essentially the same thing, which is obvious to us as developers, and sort of getting the tool to do things in the way that makes sense, that's obvious to us as developers, is the tricky part. This is highly important for building a static code analysis tool, and it's often overlooked because it's not the technical side, it's the UX side of things. So any tool, as I said, static code analysis can't be right. There's no way for static code analysis tools to present correct results. So it's all about trade-offs, and there's two ends of the spectrum. One of the spectrum is we report every potential problem. And so if we don't report it, you can be sure there's no problem. Which, on the other hand, means that there's 99% or 95% in real-world scenarios of false positives that you need to sift through. And in practice, this usually doesn't work out so well because people stop being interested in looking at the results because no one wants to sift through tons of false positives all the time. The other end of the spectrum is if we report something, it's worth looking at because it's practically guaranteed to be a true positive, which is usually harder to do, but is often in practice the more worthwhile approach. So this is my categorization of static code analysis tools in terms of their sophistication of what they can do. The basic level is sort of text-based grep and Linux or Unix command line tools. Then there is structural matching based on an AST on top of that. And then there is simple flow-based stuff, usually with merging and k-limiting, which does add simple flow support, but is very limited in terms of, well, it has high rates of false positives, false negatives, and all the scenarios I showed will get this kind of tooling out of step. And then there is what I'd call full-blown support with sophisticated optimizations that go way beyond what I can tell here, but that address the tricky parts and go beyond merging and k-limiting in order to have more precise results, which is very tricky to do, but yeah, that's sort of the highest level of sophistication as I see it. So to sum up, this is an overview of stuff that is tricky to analyze for static code analysis. Reflection, obviously. Recursion. I mean, reflection means there's strings that we need to interpret, and yeah, in the most general case, it's impossible, which makes analyzing JavaScript a highly interesting undertaking, because it's not called reflection in JavaScript, but JavaScript essentially does reflection in every single line of code. Recursion, obviously, polymorphic calls, as I said. Aliasing, sure. Then there's accessing maps by value, with literal keys. So if you put stuff into a map and get it out in a different place, correlating that can be tricky. Correlating conditionals, all these kind of code that use the same condition in several places, and figuring that those two are essentially correlated is one of the tricky things. And then all these niceties of framework and library awareness, and yeah. So that's it. Thank you very much for listening. And if you're interested, you can approach me. I'll be at the conference, or you can join me at the booth, or whatever. Thank you very much.